Probably many of you know this. We have to just revise for the sake of the course. Continue basic examples on probability. So last time we introduced the basic notion and one problems about that's the Ramsey, and we saw what we did is one construction or rather one argument that uses probabilistic method. So we'll do some more. Some of them are easy, some of them are slightly tricky. Okay, so let's continue.
Recording in progress.
So let us take another example. So let a and m are integers, they're at least 1, and m is at least so why we are doing all these examples is basically we want to develop an intuition how one use probabilistic method to prove many things in combinatorics rather easily. You can probably do these things without using probabilistic method also, but those arguments will be much involved and complicated. So this is often shorter. It's possible to color each edge of the graph KNN. Now you know what KNN is. Two color, red or blue, such that no KNN subgraph will be monochromatic. So this is another, like many times in probability theory, you will be seeing some problems like the problem does not involve anything about probability. That is the beauty of probabilistic method. So problem looks like, see this problem is saying that you have a graph KNN. This is the graph KNN, right? All possible edges are there. This graph we have seen many times in the graph theory lectures. And there is some parameter for the m, and this problem simply says that there is a way to color these edges by either red or blue such that no subgraph which is same as KMM, taking m from this side and m from this side, will be monochromatic. So problem does not involve anything about probability, but probabilistic method offers you to solve it efficiently. Okay, so how do you address it? I think the idea is kind of clear from the last example that we did. Right. So first let us see that first thing that you should notice how many such KMM subgraphs appear in K. That's easy because you can take any m from here, any m from here, and that subgraph will be one of the copies, right? So this number is clearly n choose m times n choose m. So n choose m square. Now what's the next step? So if you fix any such KMM subgraph and color the edges randomly. Call this subgraph maybe H. Fix any subgraph H randomly using red or blue. Then what is the probability that the subgraph will be monochromatic? Right? So probability that H will be monochromatic that's very simple, right? How do you estimate that? This KMM, that subgraph, has M square edges, right? And it will be monochromatic when all the edges are colored either by red or by blue. So how many possible ways to color them? There are M square edges. So there are exactly 2 power M square different ways to color them. And among that, 2 will be monochromatic. Either all of them are red or all of them are blue. That's equal to 2 power 1 minus M square. So by union bound, the probability that any one of the KMM subgraphs will be monochromatic. This will be what? One subgraph will be monochromatic with this much probability. And you are taking a union bound over so many subgraphs. Right? So that's very easy. So that probability is nm squared times 2 power 1 minus m squared. So what we need to prove? You will need to prove that this probability is strictly smaller than 1. If we show that, then what is the complement event? So this probability is over what? We are randomly coloring and finding the probability like at least one of the KM subgraph will be monochromatic. And we want really the complement event. So if we prove that this is strictly 1, then you know that this event, that if you pick a color randomly, none of this KMM will be monochromatic will happen because the complement event probability is strictly less than 1. Is it clear, the argument?
Yes, sir.
So we have to just estimate that, and that is very easy because this is simply, how much is this? So n choose m, you can, of course it is less than n power m. So this is less than equal to n power 2m times 2 by 2 power m square. So this is strictly less than. In fact, I can drop 2 itself. I don't need, n power 2m is a much bigger quantity. So I can just continue. And I know that n is this relation, right? So m greater than equal to 2 log 2 n. So log 2 n is less than equal to m over 2. That means n is less than equal to 2 power m over 2. So this means this quantity is, substitute n by 2 power m over 2. So this will be 2 power m square by 2 power m square. But notice that I have used one strict inequality in between. So that means this quantity is strictly less than 1. That's it. And notice one thing is that although we have existentially proved that there exists a coloring that will leave all the KMM subgraphs not monochromatic. It does not give you any clue how to find that color. This is a big issue in probabilistic method. It's an existential argument, but often in computer science and mathematics, you will be asked the following question: find the color, find the coloring which achieves this property. And this kind of argument does not give you any idea how to find such color. Some cases you can make a constructive argument. Some cases it is not so easy, but that's the general philosophy. Okay, so this was two basic examples from probabilistic method. So now we'll just revise a few things that probably you already know from other courses. So the notion of independence, A, B. I need to revise it because I guess there will be some people in the group who is not doing that BSc probability course. So I'll just quickly revise these things. So A and B are independent. This means probability that A intersection B is probability A times probability. We all know these things. And we also need the conditional probability. Probability of A intersection B is.
So can you go back to the last page for a second?
You mean the probabilistic method?
Yes, sir.
Today's page or yesterday, last class page?
No, this page only, little bit down. You wrote n choose m squared into 2 to the power 1 minus m squared, right?
That's right, yeah.
You
The
wrote
2 I
equal.
eventually dropped because this numerator is so big. Even without 2, it is a strict larger.
No, so my doubt is in the n choose m squared into 2 to the power 1 minus m squared. You wrote by union bound the probability that any one of the k m comma m subgraphs will be monochromatic is equal to that quantity. But wouldn't it be will there not be a less than or equal
Okay,
to
this
sign?
is the atmosphere, right?
Okay, yeah. Yes, so that was my clarification.
Okay,
Thank
this
you,
is
sir.
technically speaking, this is atmosphere. You're right. Thank you. So just revise this basic principles. So it's like most of you are comfortable with this notion of independence and conditional probabilities. Is there anybody who wants to revise it? Or I don't know how many of you are doing that course. So is there anybody, for example, in today's list who is not from the BSc group who is doing the probability course, and like any MSc student, please tell me who is not doing that course. Is there anybody here? So all of them, because I do not know like what is your background. That's why I'm asking. Okay, so here then, if you all are familiar with this notion of conditional probability and independence, so you can just practice a few problems. everything. So this is a homework left to you. So I do not want to do this because I guess most of you know. But please revise your memories because in exam some questions can be asked from these things. Okay, so we quickly then revise Bayes' theorem also. These things look very simple, but when you have to apply, sometime it could be tricky. And if you are not refreshed your memory, you can be in trouble in the exam. Because the final exam will be in CMI. It will not be a take-home exam or like an online exam. So let's say that A and B are mutually exclusive event, and A union B is a full sample space. This is a sample space. C be any event. Then probability of C. So what is the probability of C? So the event C has to intersect A and B, right? Because A and B union the whole sample space. So the probability of C is basically probability of C intersection A plus probability of C intersection B, because A and B are mutually exclusive. So that's equal to probability A times, sometimes I'm writing PR, sometimes I'm writing P. So this is the Bayes theorem. Proof as we wrote, it's immediate. So also look at the generalization. So I'll just leave this as an exercise. Look at the generalization. Generalization means instead of two event, you will have like K event, and similar way you will write. Practice problems. By the way, do you all know that you have to come to CMI for the final exam? It will be sometime in May.
Yes, sir. We received a mail.
You received mail? Okay.
Yeah.
Unless COVID dramatically changes. Okay, so this was like revised from our 10 plus 2 plus, but the probabilistic method was new, at least people who have not done advanced probability. So let's look at this notion of expected values. So let me just revise with a random variable. Usually denoted by X. This is a map from the sample space to reals. So here, everything is finite for me because I will not bring this notion of integration on some probabilistic space. That probably you are doing in the other course of probability. So here, our spaces are all finite. So I'm just talking about the finite probability spaces.
We consider countable spaces. Like
Someone said anything? Vijan? I cannot
Yes,
hear.
sir,
Your voice is
I said, is it finite or we also include, like, we also talk about countable spaces as well, like discrete places.
It's finite. For me, it is just finite.
Okay.
Because I will be doing applications from combinatorics and graph theory. So everything is finite for me. But as you can say that most of these notions can be extended. Probably you have seen also. So if you have two random variables in the same sample space, then you can define their sum, just the natural way. And you can define their product just like a function. yeah, the reason I don't want to go to the infinite because there is no game in this course. Ultimately, all the examples will be finite. So recall the expectation definition. So let's say S be the set of all the values that the random variable takes. So the expected value of a random variable is the value it takes times the probability that I'm just revising very basic things. Most of you, I guess, know it. So this is the expected value of a random variable. This quantity somehow is of immense interest and immense importance, although it looks very simple. So look at the definition. So definition is very simple. So this is the probability that the random variable gets the value I, and I multiply it by the value itself. So this is like weighted average. That's the expected value of the random variable. Let me just write one useful form. So what is the probability of x equal to I? That's really the cardinality of the set of u in the sample space such that xu equal to I divided by the size of the sample space. So if you substitute that, then it will be I times but what is this quantity? So this quantity is clearly summation of xc where u belongs to the sample space. This is just another way of writing it, which is quite useful. Okay, so we all know the expected value of a random variable. What is most useful here is the linearity of expectation. So if you have just two random variables, x and y, linearity of expectations means expected value of x plus y is just the sum of the expected values. So notice one thing is that this relation does not depend on the fact whether xy is dependent or independent anything. So this is the most beautiful consequence of this equality. It doesn't matter how x and y are related, this linearity of expectation is always true. And there is nothing particular about two random variable. You can take k random variable and then it's just summation of expectation of k random variable. And if you just multiply by some scalar, it's naturally scalar into this. These two are the principle of linearity of expectation. So C is an scale. So what is the proof? Proof is just one line. Because what is E of x plus y? Just use this formula, 1 over mu x plus y with the value. Yes. So that's and this is immediate. Yes, it's extremely innocent looking property, but you will see that in most of the complicated examples, this beautiful property of linearity of expectation plays a very crucial role. So it is important to have a feeling how you in fact use this principle. I guess today's class could be a shorter class because I have some part went to the last class, and I guess the probability will get over today mostly. So let's see some applications. So we all know what is a permutation, right? A permutation is usually denoted by, let's say, pi. So this 1 to n, and 1 will be mapped to, let's say, p1, 2 will be mapped to p2. So this is a permutation from the symmetric group. It's a group of all permutations. If you do not know what a symmetric group is, doesn't matter. It's a collection of all permutation, and with the composition of permutation operator, it forms a group. That group is called symmetric group. So the cardinality of Sn is n factorial. So this is the notation for the permutation that we use throughout the course. Okay, so let's. So in particular, this is I, and I goes to Pi. So here is the definition. I is called a valley if Pi is less than Pi minus 1 and Pi is less than Pi plus 1. Right? So this is the Pi, and this is Pi minus 1, this is Pi plus 1. If it happens to be the case like Pi is smaller than Pi minus 1 and Pi plus 1, you just simply call that number I to be a value. Yeah? Definition of value is clear?
Yes.
So the question is, so pick a permutation pi independently at random from Sn. Compute the expected number of values in pi. Okay, so this is the question. Question is very simple. I just uniformly pick a permutation from the set of all permutation. It should be uniform. How do you attack this question? Let's just try. Step by step, how do you attack it? Let's say using our notion of the probability that we have just learned. Anybody like to volunteer for this proof?
So I guess we could define random variable, indicator variables,
Exactly.
which are one if the corresponding a number in the permutation is a valley, their
Right.
sum is the random variable we want, and then we can use linearity of expectation.
Right. So it's correctly pointed out. So my random variables will be like n random variable, right? Any of these n numbers could be valid. So I'll for with each such number I will associate the random variable. Just notice one thing that I could be a value if I lives between 2 to n minus 1. N and 1 cannot be a value. There is nothing left to 1 and there is nothing right to n, right? So let y2, y3, yn minus 1 are the random variable associated points 2, 3 up to n minus 1. What is the meaning of this random variable? As we said, so yj is an indicator random variable. Is 1 if j is a value and 0 otherwise. So these random variables meaning like you should always understand the experiment. What is the experiment? You are uniformly sampling the permutation from all permutation, right? That is your experiment, and this is the outcome. That's a random variable. Okay, so the number of values, total number of values is given by another random variable y. That is the sum of all these random variables.
So if I show the definition of value, what's it?
Say it again, Rumi.
So the definition of value, can you show that what's it?
You want to see the definition again?
Yes, no, why can't one be a value?
One cannot be a value by the definition because there is nothing left to one. The left
Also, one as in the position one, not the P1.
No. So this I is the position I, not the pi.
Okay.
I is called value if pi is smaller than pi minus 1 and pi plus 1. So by definition, 1 and n cannot be value.
Okay.
So now what are we trying to compute? We want to compute expected value of the random variable y, and that's by linearity of expectation is sum of each. Yeah. Now let's someone else, not Gautam, someone else should tell me what is the expected value of the random variable yj. Let's see.
Probability that it is a valley.
Sorry. Say it again.
The ith position is a valley. That is the expected value.
Yeah, but what is the expected value? That is the event, right? J position is a value, is the event. What is the expected value of that event? That's the question. EYJ. That we need to compute and add. Is the question is clear? What we are trying to compute?
Yes, sir.
Okay, so try that. So up to this is the framework. Like you have learned the principle, generality of linearity of expectation. We have associated it with our problem statement, and now we want to compute the value of each of the random variables and add them. Can somebody say how to compute E of yj? Work it out and tell me. That's a simple question, right? I have sampled a permutation uniformly at random. What is the probability that the element associated with j by the permutation is smaller than the element associated with j minus 1 and j plus 1? That's the probability I want to estimate. So the goal is to compute this. Who has computed?
Sir, is it 2 into n minus 2 factorial divided by n factorial into 2 choose 2, 3 choose 2?
Can you just simplify? Can you simplify it and tell me? Then I'll understand.
Okay, sir.
Because such a big expression, I'm not able to follow.
Sir, I'm getting n minus 1 by 2n the whole squared.
Say it again. You are giving the answer for the complete sum, right? The entire
No, sir.
sum you are
No, sir, just for like
for this much. For this
yes,
much
sir.
only. What is your number?
So basically, we have to show that the number associated with j is less than both its neighbors. So for one of its neighbors, I got n minus 1 by 2n. So for both of its neighbors, we'll treat it as independent. So we multiply the probability. So I get n minus 1 by 2n the whole square.
So you are giving me the you are telling me the value of that e of yj itself, right?
Yes, sir. Yes, sir.
Now tell me the value of concrete
N minus 1
minus 1
by 2n
by 2
the whole square.
whole square of this.
Yeah.
I think something is wrong in your argument. How did you get it?
I mean, I'm not completely sure, but this is the answer I'm getting. I mean, it might as well
Just
could
check
very
your
well be
argument.
wrong.
You will figure out what is wrong in it. No, this is not correct.
Is it 1 by 6?
One, you are telling me the expected of yj.
Yes.
You are almost there, but not quite. It's not 1/6.
Should be 1 by n
1 by
minus
3.
1 by
3. 1 by 3.
just 1 by 3, right?
Yeah, just 1 by 3.
Yes, that's correct. This is independent of it, the expected value. Now, what is your argument?
Just take 3 values and all the permutations. So you get 6 permutations, and out of which 2 of which will be a value. So 2 by 6 is
Exactly.
1 by 3.
So yeah. So everybody got that argument. You don't need even like a lot of calculation. So what is said that there are 3 values associated with for this point basically. This is I minus 1, I plus 1. What is said that you take 3 values and then the smallest value you associate here, the middle one. 3 distinct values and the smallest value associate here, and the other 2 values you permute. among these two terms. So that gives you like 2 factorial, and all possible way you can arrange it, it's like 3 factorial. So that's the very cute way to see that it is 1/3. There is a more elaborate way also one can see it. So that I can just write, but this is a better way. If you are not convinced and if it is too quick for you, you can do the more brutal calculation also. Everybody understood what is the argument here? But there is a more brutal way to see it. So there are n factorial way to permute everything. Among these things, I want to choose permutations for which the middle one at the ith location is smaller than its neighbor. So I can choose any of the 3 numbers, just the way he has taken the set, and that defines one minimum that I place in the middle, and the rest, the other 2, I can permute like 2 factorial ways, and among the 3 I delete from my computation, and the rest n minus 3 I can compute in n minus 3 factorial ways. I can permute. That's it. But his argument is better. This is a more elaborate argument if you are not so quick in thinking. So that means this E of y is, there are n by 2 times 3. Now, if you go back and think like, okay, I will not use probabilistic method, then you can also try to do it without using probabilistic method, and I just leave it as a homework. Try without using probabilistic method. You will see the difficulty. Why the probabilistic method makes your life very simple. Everybody is fine with this line of argument? Or anybody has any doubt? Apratim, did you see the problem in your argument? Because I cannot talk to you the board, so I'm asking.
So maybe I can like mail you about it later.
Okay,
I mean, I understood the 1/3 argument.
Okay, good. Yeah, fine. Okay, so let's. So we are slowly getting used to of thinking in a probabilistic manner, right? Let's take more examples. This unfortunate thing about these lines of work is that there is no thumb rule. How do you attack a problem? It all depends on your intuition and your exposure to lots of examples. Because it's a bit ad hoc. How do you relate it with this kind of methodology? It's completely ad hoc. So another definition. So for a permutation pi, so pi is a permutation. Or the set sim, and I can define the stabilizer point of pi, that is simply those point I such that pi I equal to 1. This is like fixed point. Permutation has not moved this point. That means if you like that rectangular notation, so this I has moved to I. So many points will be moved to this point, and that set I call the stab set, stab of pi. So the question, these are also called the fixed point. Find the expected fixed point in a random permutation phi. Anybody can try. Particularly people who have not tried, they should try earlier. It's a very simple problem. First, think about how do you attach a probabilistic model with this question. Yeah, and then in step by step you can solve it.
So basically, what is the probability that 1 will stay in its place, 2 will stay in its place, etc. And
Yeah.
we just have to add it.
Yes, yes. But we have to go more systematic way, right? So we first define the random variables. Let y1, y2, yn are the random variables such that what is the property of the random variable? That's the main thing to do. After that, it's more like a routine work. You have to associate the random variable correctly with the question.
The number of fixed points.
Number of
Fixed points.
no. So these are the
So yi is equal to 1 if pi of I is equal to I.
right. If I is a fixed point and 0 otherwise. Then you know that the random variable you are interested is y is the sum of all y. And you want to compute the expected value of this random variable y. That is by linearity of expectation, expected value of y. Now it is very simple. What is the expected value of yi?
1 by n.
Exactly. Expected value of y1 is like 1 goes to 1 and rest can be permuted. N minus 1. So this is n minus 1 factorial by n. It's quite surprising that like very simple argument. I'll be back in a minute. Okay, so let's continue more on expectation. Again, it's a random variable, and my case is this set. Set of the values that the random variable takes. And let it's the maximum value in case. Then it's an observation just that expected value of the random variable is bounded by G. That's obvious, right? Because the expected value is I, probability of x equal to I, and that's equal to, because I is bounded by J, so I take J out, probability of x equal to I. That's equal to J. This probability of so this is a very simple observation, but it's very intuitive. Like the expected value cannot be more than the highest value that the random variable take. That's the insight you should take home. So let's see some. So remember this principle that expectation is always bounded by the maximum value of the range of the random variables. There's nothing deep in it, but let's now see some example. These examples from graph theory. Let G be a simple graph on n vertices having m edges. Then G contains a bipartite subgraph with at least m over 2 edges. It's a beautiful statement, right? So G is a graph over 1 to n and having m edges. Any graph. And the goal is to prove that G has a bipartite subgraph with at least m over 2 edges. Now think about this problem. How do you prove such statement?
The expectation of number of edges in a bipartite subgraph is greater than n by 2.
Say it again.
So the expectation of the number of edges of a bipartite subgraph will be greater than n by 2.
Right. So if we can, exactly, so that's a good idea. So if we can prove that the expected number of edges in a bipartite graph will be at least m over 2, then we know that there will be a subgraph, bipartite subgraph of number of edges is at least m over 2. But how do you compute that expectation and argue that? Firstly, how many bipartite graphs you can construct from G? How do you construct a bipartite graph from G? You can, the most logical way to do that, you can take the vertices of G and you can split into two parts, and then you look at the edges that is flowing across the two cut, ignoring the edges flowing inside the pieces, right? That means if I take like A and B to disjoint non-empty set from the vertex set B of G, and then one side I write A and another side I write B. I just look at the edges going across these two sets, and you can ignore the edges going inside this set. There could be some edges inside these sets also, right? Here. We can ignore these edges. So this way we can form a bipartite graph from G. So my sample space will be logically all such bipartite graphs. And I have to prove that one of these subgraph will be at least so many edges.
So if we choose a random variable to count the number of edges, then the probability of that being at least m by 2 is strictly greater than 0 would suffice.
Say it again. Probability.
So I mean, if we take the random variables so that they count the number of edges.
So that means you are associating one random variable with every edges, right?
So I mean, for one edge x.
Right. Yeah, just try it. You are on the right track. So you are associating.
So I mean, the random variable x takes values in the range 1 to m.
You are doing a step jump. So basically, you are from the beginning. You are trying to looking at the sum of the random variables. So
Yes,
it's
sir,
a
that I need
better
to
way,
split. Sure.
yeah, the better way to think about it, for every edge you associate with the indicator random variable.
Okay.
That means, what is the idea? The idea is, if I pick one of these subgraph at random and you hold an edge, I want to understand what is the probability that that edge that you are holding with belong to this subgraph, this bipartite subgraph. That way you can associate a random variable with to that edge, right? Indicator random variable.
Yes, sir.
If that, right, just illustrating your ideas. So if that edge falls in this cut between A and B, then you give it to 1, otherwise you give it to 0. Then you can use this linearity of expectation principle that will tell you, okay, how many such edges are going into this cut of A and B. That's the idea, right? Yeah, I guess you said.
Yes, sir.
Yeah, more or less this. Yeah. So first, let's fix the sample space. What is our sample space? The sample space is that all such bipartite graphs. Let's go step by step. This is a sample space. Because what is my random process? That I have to understand. My random process is sampling one of these bipartite subgraphs from the sample space of all bipartite subgraphs. Now, what is the cardinality of this? You have to make like this A and B are non-empty set, right? So for example, that for the A side, if you build, you can take one vertex, or you can take two vertex, or you can take n minus 1 vertex, and that gives you 2 power n minus 2. But I mean, this name of A and B are arbitrary, right? So I mean, total number of graphs will be half of this. I mean, I don't distinguish between left and right in this question. It's just like splitting, which way I can split. So this will be 2 power n minus 1 minus 1. So this is my sample space. Let's just split the vertex and construct this sample space. Is it clear how I calculated the sample space size?
Sir, I have a doubt.
Yeah.
Like if we have what's a subset of B, it's like we consider the subgraph of A and a subset of B, then that will also be a bipartite subgraph.
Yes. So you are saying that you no need to split the entire vertex set, right? That's the thing you are trying to say.
I mean, so like if we so like I don't see like how it will be like choice of A like determines B. Like it could be like,
I have taken the full. I understand your confusion, but I am taking the full split. I mean, the vertex set I split into just two pieces, A and B.
okay, yes, sir.
if I just able to prove by the probabilistic argument that I am true in that set, then you know that I am true in the whole graph.
Okay, yes, sir.
Right? So what you are saying that because I am kind of having a assumption that A union B is V. That is your objection.
Yes, sir. Yes.
Yeah. So, but I can choose the sample space as I wish. All I have to say that in that sample space, this event happens.
Yes, sir.
Okay. So good. So now, so let's take, yeah. So now with M edges, this is the most tricky part in this probabilistic method because you have to frame the game in a nice way. Otherwise, you will be wrong from the beginning. Final computation will be often easy, but this is the hardest part. With M edges, associate random variable y1, y2, yn such that yi equal to 1 if so every yi is associated with one edge, right? So let me associate the edges u1, e2, en. If ei is an edge in the randomly picked graph from omega, zero otherwise. So that's my random process.
Hello, sir.
Yes.
Sir, I mean, first of all, when we choose n choose 1, n choose 2, in any way the vertices, we actually partition the set of vertices, right? But we do not see how they are connected. I mean, are we sure this falls?
The connection is defined by the graph G. Graph G has its edges, right?
Okay, sir.
So when you partition, what will happen that some of the edges will come into this cut. This is called a cut in graph theory. And some of the edges will be here, some of the edges will be here. I delete these edges because I am interested in the bipartite graph. And I am interested only the cut edges.
Oh, okay, sir. So when we say yi is equal to 1, then we mean that ei is a cut edge.
EI is a cut edge, exactly.
Okay.
That's the reason I wrote it is in the randomly picked graph from my sample space omega, which is itself like a set of bipartite graphs. So that means it's a cut edge.
Okay, sir.
Okay. So what is the probability that, let's say, u1 equal to 1?
Sir, but I'm actually not sure if we randomly choose a say, partition of A and B, then that is indeed bipartite.
No, that is not bipartite. I am forcing it a bipartite graph out of it by keeping only the edges that is flowing across A and B and deleting the edges that is flowing inside the set A and inside the set B. Of course.
Sir, but if such cut edges do not exist at all for a particular selection,
then it will be empty.
Okay, sir.
That's not a problem. So what is the probability that y1 equal to 1? This is 1 if, how can it be 1? Because this u1 has two endpoints, right? v1 and v2. It can be only 1 if v1 in your selection go to one side and v2 your selection go to other side. Then it will be a cut edge. This is important to understand. How can this edge u1 be a cut edge in your random process? There's only way it can be a cut edge. Like v1 you have chosen in the left set or one set, and v2 you have chosen in the other set. You do not put both of them in the same set. Right? And rest of them you do not care. The rest n-2 vertex, you can place them either here or here. that does not disturb the indication of this edge. So every other vertex you can put in two ways. Either you can put it in the set A or you can put it set B. Or rather, either you can put it in the V1 side or you can put it in the V2 side. Right? So this is basically, so this is my, so I am sampling my graphs from my sample space omega. So this is the H that I'm sampling from the sample space omega. And that sample space size is 2 power n minus 1 minus 1. And this edge is flowing across the cut. Right? And others vertices can choose either V1 side or V2 side, doesn't matter. That means every vertex has two possibilities. So that means it is 2 power n minus 2 by 2 power n minus 1 minus 1. Right? So this is 1 by 2 minus, and it's dividing out. Which is more than half. That means the expected value of the y is summation of pi. These are the h indicator variables. It is at least n over. This example was little tricky than the earlier examples. So this, now once you prove that, then your conclusion is immediate. That means there exists some bipartite subgraph with at least m over 2 edges. Now, if you don't use probabilistic method, this kind of argument would be much harder. I didn't check it, but if you check, I guess there are many cases to argue such thing will be difficult. Because you have to do lots of complicated counting. And you will be prone to make mistakes. Is it clear? The argument is?
Yes, sir.
So this was more or less the main part of the probability module that I wanted to revise. Let me stop the recording.
Recording stopped.
If you have any question, you ask. Next class we'll start some new topic. That will also involve some probabilistic ideas. We'll start a new topic. So what is going on in group theory now? How much you are familiar with the group theory now?
So today we were doing quotient group.
That means, oh, you have completed this quotient group. I mean, oh, so Lagrange's theorem, all these things are over.
Yes, sir.
Okay. But have you done the symmetric groups now, by now?
Somewhat, sir.
Is it like that arting? You are following arting, right?
Yeah.
Okay, I guess so is for the today's class.
Thank you, sir.
Thank you.